A-Level Chemistry Paper 3, 2017. Anhydrous magnesium chloride, MgCl2, can absorb water to form hydrated salt, MgCl2H2O. So that's the reaction there going ahead. It's just one reason why the enthalpy change for this reaction cannot be determined directly by calorimetry, because that reaction doesn't actually go ahead. So that's a theoretical reaction. What actually happens is when the MgCl2 is put into water, it actually dissolves. Magnesium chloride is soluble, so it actually won't form that reaction at all. It dissolves. So we have to work that out by some of the methods. We have to work that out via a mathematical method. So now what we've got is we've got the enthalpy of solution, so that's the energy released minus 155 kilojoules per mole when 1 mole of magnesium chloride is dissolved in water. And then we've worked out the same for MgCl2 4H2O, how much energy is released, its an exothermic reaction, when 1 mole of this is dissolved in water. And then what we do is we draw a triangle. So we've got this reaction here, MgCl2, and 4H2O going MgCl2 4H2O. And then if you imagine coming down here is what would happen if they dissolved in water. So if I dissolved this in water, MgCl2 in water, MgCl2 here, dissolved in water to make MgCl2 aqueous, minus 155 is the energy given out when this is dissolved in water. Similarly, the enthalpy when this is dissolved in water, MgCl2 4H2O, to make the same thing, to make the same product, is minus 139. So we've got the enthalpy change for MgCl2 dissolved in water, we've got the enthalpy change for MgCl2 4H2O dissolved in water, and they're both going to make aqueous dissolved magnesium chloride here. So now, minus 155 from here to here is minus 155 to make dissolved magnesium chloride, and then we want it to go from here to here to make the MgCl2 4H2O. So I need to reverse this sign. So my enthalpy change is minus 155, not minus 39, but to come round from here to here and here to here to equal this enthalpy is plus 39. So your answer is minus 155 plus 39 is 116 kilojoules per mole. Describe how you would carry out an experiment to determine the enthalpy of solution of anhydrous magnesium chloride. You should use about 0.8 grams of anhydrous magnesium chloride. Explain how you could use your results to calculate the enthalpy of solution. So first of all, you've got to measure out an amount of water. Let's say it's 100 centimetre cubed of water. That's a good amount to use, because when we use Q, or delta H equals minus MC delta T in a little while, then that's the mass of water that you have. So M, the mass of water, is going to be 100. So I've measured out 100 centimetres cubed of water into a measuring cylinder. I'm going to have an insulated cup, so something like a polystyrene cup or an insulated beaker would be fine, so that I don't have any heat loss. And then I'm going to measure out my 0.8 grams of anhydrous magnesium chloride. There'll be a mark for saying you weigh it out and then you put it into a weighing bottle and reweigh the weighing bottle, reweigh the container and subtract the two, so you can work out actually how much has been put in. Because you might find, let's say, that only 0.7 grams is actually put in, and 0.1 gram remains in the weighing bottle. So you weigh it out into a weighing bottle, and then you add it in, and then you reweigh the weighing bottle, and by subtraction then you can work out how much you've actually added. You then record the initial temperature for 3 minutes, and then on the 4th minute you add the magnesium chloride to the water. You could stir it and then record the temperature every minute for about 5 minutes or more and plot the temperature against time. And what you're going to find is that there's no change or very little change in the temperature, and then all of a sudden it will shoot up and then come back down again. So it'll shoot up because it's an exothermic reaction, and then as the reaction's over, the contents of the beaker will start to cool. You extrapolate the two lines back to the 4th minute and you measure the change in temperature. So You extrapolate the lines back to the 4th minute. That means you extend the line, so from 3 minutes you extend to 4 minutes, and you go back from 5 minutes back to 4 minutes, and you work out the temperature change that would be happening at the 4th minute. When you've got the temperature change here, you've got the enthalpy change, you've got the mass, which is 100 centimeters cubed, assuming that we've got water is 1 gram per centimeter cubed, that's its density, that's 100 grams, and therefore you can work out Q. Then to work out delta H, well, you've got to work out how much of this you've got in terms of moles. So you take the mass that you've added divided by the MR, and we could even work out the MR of magnesium chloride at 95.3. We've got 8.39 times 10 to the minus 3 moles. So I've worked out moles as mass over MR. I know that's the number of moles that I've got. I've got to take the enthalpy change, Q, and I have to multiply it up to work out what the enthalpy change would be if I had 1 mole instead. So what I do is I take 1 and divide by this number, and this is the factor that I'm scaling up by, 119.9. So I take 1, divide the number of moles that I've got into 1 divided by this number gives me the number 119.19, and therefore my enthalpy of solution, the energy produced when I dissolve 1 mole of anhydrous magnesium chloride in water when I make a solution of it, is whatever value I had before multiplied by 119.19. Question 1.4. Anhydrous magnesium chloride can be formed by the direct reaction between its elements. So I've got magnesium solid, chlorine gas making MgCl2 solid. The free energy change, so Gibbs free energy change for this reaction, varies with temperature as shown below. So I've got temperature in Kelvin, and I've got Gibbs free energy change in kilojoules per mole. Use the data to plot a graph of free energy change against temperature on the grid opposite. Calculate the gradient on the line on the graph. So we've got to put free energy change against temperature. So if we look at that, so free energy change is down the y-axis and temperature along the x-axis. So Gibbs free energy change against temperature. So these values are coming down, so you actually have a look, it's minus 592 going down, and the temperature is going up. So I've plotted with the origin here, so I can come down on this side, and I can go across, and I've started from 240 and minus 592, and I've plotted the points on the graph and drawn a straight line. There's a mark for plotting the five points in the straight line and then working out the gradient. So that's the change in y divided by change in x. So you take 592.5, here is the top point, high point, going down to minus 602. So take away minus 602. So minus 592 minus 602. And then so the change here, you're actually measuring the change, so you can ignore the signs actually, you're just measuring the change, so the change between 593 and 602, and then you're measuring the change along the bottom from 240 to around about 298. So when you work those two out, it works out as 0.167. It's in kilojoules per Kelvin per mole, it's in kilojoules here, because Gibbs free energy changes in kilojoules, kilojoules per Kelvin per mole. So to get that into joules, we're going to have to multiply by 1,000. So to get kilojoules down into joules per Kelvin per mole, then a large unit value down into a smaller one, you multiply by 1,000. Now, y equals mx plus c. The y value equals m, which is the gradient, multiplied by x, whatever's on the x-axis, plus c is a constant. So Gibbs free energy change delta G equals delta H minus T delta S. You could rearrange that slightly so you can see how it matches up with y equals mx plus c. Delta G is up the y-axis, so that's correct, equals mx. The x value is T. So T delta S, or delta S times T, minus and then plus delta H. Well, the delta H is a constant. So you can see here, this is the y bit, delta G, T is the x bit, and so this minus delta S is the m. that's the gradient. So the gradient is minus T delta S. So delta S equals minus the gradient, so I'll reverse the sign now. So gradient equals minus delta S. Delta S is minus the gradient, so the gradient, now I've multiplied this by 1000 to get it into joules per Kelvin per mole, is minus 167 joules per Kelvin per mole. Question number 2. Concentrated sulphuric acid reacts with alkenes, alcohols and sodium halides. Name the mechanism for the reaction of concentrated sulphuric acid with an alkene. So the double bond attacks the sulphuric acid and sulphuric adds on, so it's electrophilic addition. We'll have a look at that mechanism now and understand electrophilic addition. So what actually happens here is the double bond attacks the H+. That's because that's a polar bond. Oxygen is more electronegative than hydrogen, so it gets a delta minus, and the H gets a delta plus. So the electrons in the double bond to that H. And then the electrons here move onto the O because the H is bonded onto the alkene, so the electrons move onto the O. That's going to create an O minus because electrons have moved onto the O, so it creates a minus charge, and there's a pair of electrons there from the bond on the O. There's a plus charge here because the hydrogen is added onto the end, so this is the major product. So the hydrogen, will it go to the left-hand carbon or the right-hand carbon? It goes to the carbon with the most number of hydrogens to leave a stable secondary carbocation. That carbon is charged plus because electrons have moved away, and that carbon is charged plus also, you could say, because it's not got enough bonds and electrons are in bonds, so it's short of electrons, it's short of minuses. So it's got a plus charge, and that's a stable secondary carbocation. The C with the plus has got two other carbons bonded to it, so it's secondary, not primary or tertiary, and it's stable because the two methyl groups repel electrons and reduce the size of that plus charge. Now the lone pair of electrons from this ion that's made attack the C+, and it bonds on like this. This is an electrophile and an electron pair donor. Here, an electrophile, and because two reactants have made one product, two become one, and therefore it's addition, electrophilic addition. Draw the structure of the minor product, the reaction between concentrated sulphuric acid and propene. So instead of the H bonding to the left-hand carbon and forming a stable secondary carbocation, as normally happens, the major product, it could, in theory, a small amount could do the opposite. So the H could bond here and leave the plus on carbon number 1, and the OSOOOH could bond onto carbon number 1 instead of carbon number 2 via a primary carbocation. That's less stable than the secondary carbocation, but it could occur in small amounts, and that's called the minor product. So here the OSO3H, or you could draw it out like this again, but instead of it bonding the OSO2OH, instead of bonding to the C carbon number 2, it's bonded to carbon number 1, and then you've got CH2CH3. Explain why the product in your answer is the major product. So we've said that already. It's a stable secondary carbocation. It's more stable than the primary carbocation. If you were to make incidentally a tertiary carbocation with 3 carbons around the C+, that would be even more stable, because the reason why the methyl groups repel electrons. It's called a positive inductive effect, and it reduces the size of the charge on the C+ and makes it stable, but all you need to say is that the methyl groups repel electrons. Butan-2-ol reacts with concentrated sulphuric acid to form a mixture of 3 isomeric alkenes. 2 of the alkenes are stereoisomers. So let's have a look what happens. Well, first of all, butan-2-ol looks like this. And what concentrated sulphuric acid does is it removes water. It removes an OH, and from a neighbouring carbon it removes an H. So the water is coming from here, an OH, and on a neighbouring carbon an H. It could do it the other way. It doesn't know left from right, so it could take an OH from this carbon and an H from carbon number 3 instead of carbon number 1. So it can take the HOH from here in between carbon number 1 and carbon number 2, and that will leave a double bond then in between carbon number 1 and carbon number 2. It will make but1e. Or alternatively, the OH and the H could come from carbons number 2 and carbon number 3 and make but-2-ene. And but-2-ene would then have stereoisomers, geometrical isomers, E and Z isomers. So let's have a look at the skeletal formulas. So I could have but-1-ene, where the double bond is in between carbon number 1 and carbon number 2, but-1-ene. I could have but-2-ene, and I'm going to have two forms of that. I could have but-2-ene, which would be E-but-2-ene, and I could have Z-but-2-ene. So E, there's the double bond, and here's the methyl group 1 on one side and 1 on the other, and here is Z-but-2-ene with the two methyl groups going down on the same side. You could have them going up, so you could draw this in any kind of shape you wanted to. As long as the methyl group's going up and the other one's going down, you could have it this way, down and then going up if you wanted to, and similarly you could have both of these going up. As long as there's the two methyl groups are on opposite sides of the double bond for E-but-2-ene and on the same side of the double bond the Z-but-2-ene, that will get you the marks. This is a little known thing, but concentrated sulphuric acid can act as an oxidizing agent, so it can turn butan-2-ol into a ketone. Now the best way of doing that is through acidified potassium dichromate with a little bit of dilute acid. That would be the best way of turning a secondary alcohol like this, a secondary alcohol with the COH in between two carbons. So the COH is bonded to two carbons, so that as a secondary alcohol with potassium dichromate and a little bit of sulphuric acid would turn that into a ketone, a C double bond OH, and that H would be released. Similarly, if the OH were at the end on carbon number 1, it would, a primary alcohol, it would make an aldehyde, and then further reaction with potassium dichromate heated for a prolonged time called reflux would actually turn that then into a carboxylic acid. So the best way of oxidizing a secondary alcohol into a ketone or a primary alcohol into an aldehyde and then into a carboxylic acid is to use acidified potassium dichromate, which would go orange to green in the process. However, a little known fact is that concentrated sulphuric acid can do that on its own. It's not as strong an oxidizing agent as acidified potassium dichromate, but it will do it. It will do it to a slight amount. So you could get, just with concentrated sulphuric acid on its own, it needs to be concentrated sulphuric acid, and as I say, it's not as strong an oxidizing agent, it's not going to do it as well as acidified potassium dichromate, but it could turn that into butan-2-ol with a butanone, butan-2-one or butanone. It can only be an one, a ketone. It can only have a carbon to oxygen double bond at carbon number 2, as if it was at carbon number 3, you'd just start labelling from the other end. That would be butan-2-one as well. So butanone, we can make that. The role of the sulphuric acid, well, it's removed H's. It's taken an H off there to make a C double bond O. It's taken an H off there and an H off there. Something that removes H's is called an oxidizing agent. And how you would separate then a byproduct, well, if you've got more than one liquid, you'd use distillation. Before we do the next question, let's just do a little bit of revision around halides. If we have concentrated sulphuric acid with sodium fluoride, a fluoride, it makes white steamy fumes of hydrogen fluoride and something called hydrogen sulfate, sodium hydrogen sulfate. In this case, if you have a look at the F has received an H. It's actually received an H plus because F will be F minus, H plus F minus. So it's received an H plus from the sulphuric acid. So the sulphuric acid has donated an H plus. Something that donates an H plus is called an acid. So the sulphuric acid is acting as an acid to turn F minus into H plus F minus, or HF. Similarly, exactly the same thing with sodium chloride, but you'd make hydrogen chloride as white steamy fumes, and sodium hydrogen sulfate again, and again the sulphuric acid is acting as an acid, donating H plus to the Cl minus to form H plus Cl minus, or HCl, hydrogen chloride. And the reactions stop here. The sulphuric acid isn't a strong enough oxidizing agent to do the next step. Let's have a look at sulfuric acid acting as an oxidizing agent. So with sodium bromide, the same thing happens again. We get the sulfuric acid acting as an acid, forming HBr as steamy fumes and sodium hydrogen sulfate. But then we get another step. The sulfuric acid, the concentrated sulfuric acid, is a strong enough oxidizing agent to be able to take this HBr and to oxidize it. Let's work out what oxidation is. In here we've got H plus Br minus, so the oxidation state of an H is usually +1, unless it's with something like sodium hydride, NaH, where the sodium is in +1 and the H is as -1. Usually a H is as +1, and so the Br is -1 oxidation state. When it's on its own as an element bonded to no other atoms, it's 0, so it's gone from -1 to 0. It's been oxidized, so the number has gone up from -1 up to 0. It's been oxidized. And bromine is a brown liquid, but actually, if it's slightly warm, it will form a brown-orange solution or orange fumes. So it can form orange fumes or an orangey solution, a browny-orange solution. So it's normally a brown liquid on its own, but if it's in solution, it might be slightly orangey, a brown solution, orangey fumes. It will also produce sulfur dioxide, which is an acidic choking gas, and some water as well. In this case, the sulfuric acid has acted as an acid, but now it's acted as an oxidizing agent, oxidizing the HBr to Br2. Sodium iodide, similar reaction again, the concentrated sulfuric acid making hydrogen iodide as steamy fumes, white steamy fumes, sodium hydrogen sulfate, it's acting as an acid, and again, just as in the case of HBr, it can go further. So the concentrated sulfuric acid can act as an oxidizing agent and oxidize the H plus I minus in there, -1 oxidation state. On its own there as an element I2 not bonded to any other atoms, oxidation state is 0, -1 up to 0, it means it's been oxidized, and it forms I2. Now that's a black solid, so that's a black solid, and it'll also make hydrogen sulfide, which smells of bad eggs. It's in stink bombs, hydrogen sulfide, and some water. It can also at the same time go again another reaction. You don't need to know the equation for that, but it can actually make a yellow solid called sulfur. So it can go a little bit further and oxidize this hydrogen sulfide to form sulfur. In this case, it's acting as an oxidizing agent because it's oxidizing the H plus I minus to make I2, oxidation state -1 to 0. A little bit about chlorine to remember. Chlorine in water will make hydrochloric acid and something called hypochlorous acid, an equation you need to know. It makes a green solution, and the green colour in the solution is any leftover chlorine. That's a green gas. So if you're asked what the green colour is left in this solution, why it's still green, because each of these are colourless, hydrochloric acid and hypochlorous acid are colourless, it's because there's usually some excess chlorine dissolved in the water. In bright sunlight, it reacts with water to form hydrochloric acid and oxygen, and chlorine is used to treat water and kill bacteria. Common question is, chlorine's toxic, so why is it put in water? How can we get away with it treating water if chlorine is toxic? The amounts are so low that the benefits to our health in killing the bacteria outweigh its toxic effects. Let's have a look at the question then now. Question 2.7. Concentrated sulfuric acid reacts with sodium chloride. Give the observation. So we've already talked about the fact that sulfuric acid acts as an acid in the first instance, and with sodium chloride and sodium fluoride it won't act as an oxidizing agent. It's not a strong enough oxidizing agent to be able to turn Cl- into Cl2, so it only acts as an acid with sodium chloride and sodium fluoride. Observation, white steamy fumes, hydrogen chloride. Role of sulfuric acid is an acid, so it can only be an acid, act as an acid with sodium chloride and sodium fluoride, because as we say, the concentrated sulfuric acid is not a strong enough oxidizing agent to turn Cl- -1 oxidation state into chlorine gas Cl2. However, with sodium iodide and sodium bromide, it is a strong enough oxidizing agent to turn Br- into Br2 and I minus into I2. So observations, the black solid is iodine, a black solid as we've seen previously. The yellow solid, if it were to make a yellow solid, would be sulfur. It's making a gas with the smell of bad eggs. That's a clue. That's your hydrogen sulfide. Hydrogen sulfide as a gas. Question 3. Benzoic acid prepared from ethyl benzoate. There's a reaction there. Add 5 cm³ of ethyl benzoate. We've been given a density and an MR and a volume. So density is mass divided by volume. We've clearly got to work out the mass of ethyl benzoate, otherwise we won't be given density and a volume. To 30 cm³ of aqueous 2 mole decimeter cube sodium hydroxide. So we've been given a volume and a concentration, so we need to work out moles there, because concentration is moles divided by volume. We could also work out number of moles of either of those, because we've got the formulae. Add a few anti-bumping granules and attach to a condenser to the flask. Heat the mixture under reflux, so you're going to heat it in a prolonged manner, so heat it for a while. In actual fact, you're going to heat it for half an hour. It tells you how long you're going to heat it for to ensure the reaction completes. Allow the mixture to cool. Pour 50 cm³ of hydrochloric acid into the cool mixture. Filter off the precipitate of benzoic acid under reduced pressure, so you're going to use vacuum filtration. Suggest how the anti-bumping granules prevent bumping during reflux. They prevent large bubbles from forming. Show by calculation that an excess of sodium hydroxide is used in this reaction. Right, we're going to have to do some calculations. We already mentioned that we've got a volume and we've got a density of ethyl benzoate. So density is mass divided by volume. Let's work out the mass. So density 1.05 equals the mass divided by 5. Mass is 1.05 times 5, 5.25. So I've got 5.25 grams of ethyl benzoate. Now with the same thing here, so centimeter cubed and volume, so I've got concentration equals moles divided by volume. That should be an equals, sorry. Concentration equals moles divided by volume. So 2 equals moles divided by 0.03. Look what I've done there, 30 centimeter cubed. I've converted that into decimeter cubed. It needs to be in decimeter cubed. Concentration is moles divided by volume in decimeter cubed. So I've taken centimeter cubed into decimeter cubed, a small unit into a larger unit, centimeter cubed into a larger unit, decimeter cubed. I've divided by 1,000. So 30 divided by 1,000 is 0.03. So 2 equals moles divided by 0.3. Moles is 2 times 0.03, 0.06. Now I've got a mismatch because I've got 5.25 grams of ethyl benzoate and I've got 0.06 moles of sodium hydroxide, and I need to compare the two to answer the question, show that sodium hydroxide is used in this reaction. But I've been given the MR of ethyl benzoate and I've got the mass, so moles is mass divided by MR, otherwise I wouldn't be given the MR. Moles is mass divided by MR. So moles is 5.25 divided by 150, 0.035. So I've got 0.06 moles of sodium hydroxide, I've got 0.035 moles of ethyl benzoate. I've got more sodium hydroxide than ethyl benzoate, so I've shown that and got my 2 marks for 3.2. Suggest why an excess of sodium hydroxide is used. That's to make sure that all of the ester reacts. So we've got a reaction here of an ester. It tells us that we've got an ester, ethyl benzoate, so you could say to make sure that all of the ethyl benzoate reacts. Suggest why an electric heater is used rather than a Bunsen burner in this hydrolysis. We've clearly got something that's flammable, so one of the reactants or the products may be flammable. State why reflux is used in this hydrolysis. So it doesn't allow any of the reactant to escape as a gas. So what you've got with reflux is you've got a flask, but instead of just heating the flask and allowing the gases to escape, you've got a condenser above it, so that any gases that do escape go into the condenser, cool down and drop back into the flask, and so carry on reacting. Write an equation for the reaction between sodium benzoate and hydrochloric acid. So sodium benzoate is, you've got a benzene ring with COONA. You've sort of been given that in the equation here. benzene ring with a COONA. You don't need the charges on there, and you can write this as C6H5 if you prefer to. 6 carbons in a ring, and there's a hydrogen on each of these. Or I suppose you could draw it out as a ring with a COONA. I preferred to write it as C6H5COONA and HCl. So you're going to get NaCl and you're going to get benzoic acid, this is called. So it's a benzene ring with a carboxylic acid. Suggests why sodium benzoate is soluble in cold water, but benzoic acid is insoluble in cold water. Sodium benzoate is soluble because it's ionic. So you've got a clue here that you've got a plus and a minus charge here. If something's ionic, it tends to dissolve in water because water has got polar charges, because the oxygen is more electronegative than the hydrogen. So you get delta pluses on the hydrogen and delta minuses on the oxygens in water. And so something that's ionic can form intermolecular bonds with that and tends to dissolve, whereas benzoic is insoluble because it's not polar. And the benzene ring is not polar either. So the benzene ring in this benzoic acid is not polar. The COH part is polar, but the benzene ring is not polar, so a large part of the molecule is not polar, whereas sodium benzoate is ionic. Question 3.8. After the solid benzoic acid has been filtered off, it can be purified. That's a process called recrystallization. Now, it's a common kind of question, this, and yet people lose marks again and again because they forget some of the 6 marks. Yet it's the same question again and again, and the process is the same throughout. Let's talk it through. Solid benzoic acid has been filtered off, it can be purified. So the idea is that you dissolve this in the minimum amount of a hot solvent so that it just dissolves, only just dissolves, so a minimum amount hot solvent. It just dissolves and any impurities won't dissolve and can be filtered off using reduced pressure filtration or vacuum filtration. Then when you've got the benzoic acid through in the hot solvent, you can cool that hot solvent and the crystals of benzoic acid cannot dissolve anymore because the solvent has been made cool and you've only just used the minimum amount. If you'd used too much, then they wouldn't recrystallize. But with the minimum amount of hot solvent, when you cool it down again, they'll come out of solution and crystallize, and then you can filter those off pure. At the end, it's important to wash it, so wash off any soluble impurities and dry it. Drying it means that the water is removed. Water is the main impurity. The other thing to remember is that you filter it whilst it's hot. If you don't filter it whilst it's hot, then some of the benzoic acid will start to recrystallize out if it's cold, and that will be retained in the filter paper. You don't want it in the filter paper, you want it dissolved in the hot solvent to come through the filter paper so that you can maximize the yield. Let's have a look then. So you dissolve the crude product, that's the benzoic acid, in the minimum amount of hot solvent. You don't need to mention water, you can just put hot solvent if you want. That's the liquid that it's going to dissolve in. You filter it hot, and that will remove any insoluble impurities. Important that it's hot so that the benzoic acid doesn't start to recrystallize and end up in the filter paper. You want the insoluble impurities in the filter paper, and you want the benzoic acid dissolved in the minimum amount of hot solvent through the filter paper, so that when you cool that filtrate down, the liquid that's coming through the solvent and the benzoic acid, it will recrystallize. You've only used a minimum amount and you've used a hot solvent, so not too much. The minimum amount, and the hot solvent means when it cools down you will get a good yield of the benzoic acid. Then you can refilter it under reduced pressure filtration, vacuum filtration, and you'll lose 2 marks if you don't say wash with a cold solvent, because if you're washing a hot solvent it's going to dissolve again. You just want to wash out any soluble impurities and dry, because water will be the main impurity, and we'll see that in the next section of the question. In a similar experiment, another student used 0.4 mole of ethyl benzoate and obtained 5.12 grams of benzoic acid. So if I just flick back to the original bit of the question, 1 mole 1 mole of ethyl benzoate makes 1 mole of benzoic acid. One mole of ethyl benzoate makes 1 mole of benzoic acid, but I haven't got 1 mole of ethyl benzoate. I've only got 0.04 moles of ethyl benzoate. So 0.04 moles of ethyl benzoate will make 0.04 moles of benzoic acid, the same amount. Moles equals mass over MR. So I can work out the MR of benzoic acid. I can work that out because I've got the formula of it in the original part of the question, and it will come out as 122. So moles equals mass divided by 122. Mass equals 0.04 times 122, which is 4.88 grams. Now that's the amount that I could make theoretically if I'd got 100%. So now then, what did I actually make? I made 5.12. I made more than it was possible to make. Now the only reason you could make more than it's possible to make, and the yield is 5.12, that's how much I did make, divided by 4.88 what I could make, multiplied by 100%, I've got 105%. The only reason that I can make more than I possibly could make is that there's some impurity in there, and the main impurity is water. The product wasn't dry or contained some water, and that's why it's important at the end to make sure it's dry. The easiest way to dry it, incidentally, is to press it between 2 filter papers. Question 4. A 0.1 mole decimeter cubed solution of sodium hydroxide was gradually added to 25 centimeters cubed of a solution of a weak acid HX. Now interestingly, normally I'm given a concentration and a volume, the volume of sodium hydroxide that I've added from my titration, but I've not been given the volume of sodium hydroxide from my titration, so I'm never going to be able to work out moles of sodium hydroxide added. But I have got a graph, so maybe I'm going to use the graph to work out the volume of sodium hydroxide that's added. So rather than having a titration volume, I've got this here, because I'm gradually adding it, so I'm not doing a titration as such. Graph was plotted, first reading after 20 centimeter cubed here of sodium hydroxide has been added. I've added another line here, this is the later part of the question, which we'll have a look at in a minute. I've got the acid dissociation constant, the equilibrium constant for the acid. Suggest a pH range of a suitable indicator for this titration. So that's anywhere where at the end point, the equivalence point or the end point, where the pH rises very quickly. So that's in between pH 7, because it's still starting to rise. Then it starts rising very quickly here, and then tails off at around about here, starts to tail off. So between 7 and 10, there's a rapid rise in pH. That's your equivalence point or your end point. Give the expression for the acid dissociation constant HX. So HX is going to make H plus, all acids do, and then remaining will be X minus. So HX goes to make H plus and X minus. So it's the concentration of H plus multiplied by X minus, the products, divided by the concentration of HX. Calculate the concentration of HX in the original solution. So this is where I've got a bit of a problem. So I could work out the concentration of HX if I could work out how much sodium hydroxide I've added to neutralize it. Well, I can use the graph here, because at this point here, at the equivalence point or the end point, where it rises very quickly, that's where all of the equal numbers of moles of sodium hydroxide have just neutralized equal number of moles of weak acid. So at that point, the sodium hydroxide and the acid have neutralized each other. They have just reacted in equal molar quantities, an equal number of moles. So I can read down from the graph here at this equivalence point, and it turns out to be 24. So 24 centimeter cubed of sodium hydroxide is needed at this equivalence point where the pH is starting to rise very rapidly. That's the volume of sodium hydroxide that I need to neutralize this acid. So now I've got the volume of sodium hydroxide that I've needed to neutralize the acid, and I've got the concentration. I can now work out number of moles. So 24 centimeter cubed sodium hydroxide, centimeter cubed into decimeter cubed, so going to a larger unit and divide by 1000, 0.024 decimeter cubed of sodium hydroxide, and needed to react with the acid. So I can do concentration. I know the concentration from the question. Concentration equals 0.1, that's from the question, equal moles divided by the volume. Therefore, number of moles equals these two numbers multiplied together, 0.0024. At that point, the number of moles of sodium hydroxide equal the number of moles of acid. So the number of moles of acid also equals 0.0024. I've got the volume of the acid, 25 centimeter cubed or 0.025 decimeter cubed. So concentration is moles divided by volume. Moles of HX equals the number of moles of sodium hydroxide at that equivalence point. So moles is 0.0024 divided by its volume in decimeter cubed, 0.025. I have got 0.096 mole per decimeter cube concentration of HX. Calculate the pH of the solution before any addition of any of the sodium hydroxide. So how do I do that? Well, I use the equilibrium constant. So I've got the equilibrium constant here and I've got HX. I need the concentration of acid, which I've got. And now, because it doesn't mention a buffer, there's no mention of a buffer, these two concentrations are the same. So when I make a H plus ion, I make an X minus ion. So the HX dissociates to make H plus and X minus. So if it's splitting or dissociating, splitting in half, every time I make a H plus, I must make an X minus. So the concentration of H plus equals the concentration of X minus. So I can simplify it to H plus squared. I know the concentration of HX. That's that. I've just worked it out, 0.096. And I know my equilibrium constant. I can work out H plus squared. H plus squared equals these two numbers together. Square root it, 0.00159. pH equals minus log of it, 2.8. I'm going to do it to two significant figures because the value of my equilibrium constant is to three significant figures because the value of my equilibrium constant is to three significant figures. 2.80. So I've added a 0 here so that it's to three significant figures. You can't use H plus squared if you're using a buffer, but there's no mention of buffer, so I'm fine. Calculate the pH of the solution when half of the acid has reacted. So when you've added half of the amount of acid that you need to react, half of the acid, then the pH at half neutralization point, so when you've got half the acid reacted or half of the base reacted, at half neutralization, when you've got half the number of moles of acid and half the number of moles of base that I need to react, pH equals pKa. pKa is minus log to the base 10 of Ka, and Ka is 0.000262. I've got that from my original question here. So minus log of that is 4.58, again to three significant figures because the Ka is to three significant figures. So that's my pH, so that's just something to remember. pH equals pKa, or pH equals minus log to the base 10 of Ka at half equivalence point when you've added half and half. Put both points on the line, so on the graph. 4.58 is my pH at half equivalence point. So when half of the sodium hydroxide needed is added, 24 centimeter cubed to react, half is 12 and it was 4.58, so I've put that point on there. And I've also got the pH is 2.8 when before any of the sodium hydroxide was added. In other words, before any of the sodium hydroxide is added is here, volume of sodium hydroxide added 0, and I've got 2.5 there, or 2.8 rather. Question 5. Which compound has the highest boiling point? So immediately I'm looking at that OH there. We've got an oxygen bonded to a hydrogen, so we've got hydrogen bonding between molecules of this propan 1-ol. So the way that a hydrogen bond works is that you've got an oxygen bonded to a hydrogen, or a nitrogen bonded to a hydrogen, or a fluorine bonded to a hydrogen. Then there's very different electronegativities. Oxygen, nitrogen and fluorine have very high electronegativities compared to the hydrogen, so you get very large delta minuses set up on the O, the N and the F, and large delta pluses set up on the hydrogen. So it's a very polar molecule, and then on a neighbouring molecule there's hydrogen bonding, so there's intermolecular hydrogen bonding between these two very polar molecules. The others, we've got an aldehyde, we've got a ketone, we've got an ester. Now these have carbon to oxygen polar bonds, but they're not as polar because the difference in electronegativities between the carbon and the oxygen is not as great as it is between the oxygen and the hydrogen. So even though they're polar, these bonds, then you don't get the same kind of intermolecular attraction. It's not as strong between these kind of polar bonds. You get something called dipole-dipole attractions, but they're not as strong as a hydrogen bond that's got a very polar bond in its molecule, and therefore A is the answer. 6 is a very ambiguous question, because it says what's the correct order of melting points in these period 3 elements, and it doesn't tell you whether it wants high to low or low to high. So it's difficult, very ambiguous. So assuming it wants high going down to low, that seems to be the way it's going, then what have I got? Well, argon and chlorine are gases, so they're going to have lower melting points than solids like phosphorus and sulfur. So I'm going to rule out B and D, and so I'm going to go for either A or C. So I've got chlorine and argon, so that's not going to help. Argon does have the lowest melting point because it's single atoms. Chlorine is a diatomic molecule, 2 Cl atoms bonded with a covalent bond, and so that's a larger molecule with more electrons, so that's going to have more van der Waals forces than an argon. The question is, which has got the higher boiling point then? So higher melting point, sulfur or phosphorus? And your answer is sulfur. So sulfur is a larger molecular structure than phosphorus, and with it being larger, then it has a higher melting point. So sulfur with a higher melting point than phosphorus. Your answer is question 7, which is not correct. Transition metals form coloured ions and complexes. Yes, they do. If they've not got full shells of 3D, then they form coloured ions and complexes. So an incomplete 3D shell will form coloured ions and complex ions with ligands around them. Transition metals display variable oxidation states. Yes, they do, like iron 2 plus, iron 3 plus, copper 1 plus, copper 2 plus, so forth. A ligand accepts a pair of electrons from a transition metal. No, it's the other way around. The ligand donates a pair of electrons from a transition metal to form a coordinate or a dative bond. So C is incorrect. A complex is a central metal atom surrounded by ligands. That's correct. So the answer is D. That's the incorrect statement. C, rather, is the incorrect statement. Question 8. Which table shows conditions and products for the cracking of alkanes? Which is correct? Thermal is high temperature and high pressure, but makes mainly alkenes, so A is wrong. B, thermal, slight pressure, no, it's high pressure, high temperature, so that's wrong, although it does make alkenes, so that part's correct, but slight pressure is incorrect. Catalytic cracking, high temperature, yes. Slight pressure, yes. Mainly branched alkanes, yeah. Branches and aromatics, that means ring structures. So C is correct. Catalytic, high pressure, no, only slight pressure. High temperature, correct. Mainly branched alkanes and aromatics. So the answer is C. Slight pressure, high temperature for catalytic cracking, making mainly branched alkanes and aromatics. C. Question 9. 2,4,6-trichlorophenol is a weak monoprotic acid, so that means it makes 1 mole of it makes 1 mole of H plus ions. Kw is given at 298K. 298K is normal room temperature, but I think that's a red herring, that won't matter. What is the concentration in moles per decimeter cubed of hydrogen ions in a 2.00 times 10 to the minus 3 mole solution of 2,4,6-trichlorophenol at 298. So the temperature's staying the same. So what have we got? What do we know? Well, we know Ka, and that'll equal the H plus squared. We're allowed H plus squared because we've not got a buffer. So we can have H plus squared divided by the concentration of 2,4-trichlorophenol, which we have. Okay, so we've got the Ka equals H plus squared divided by the concentration of 2,4,6-trichlorophenol. Put the numbers in. H plus squared we can calculate as 5.02 times 10 to the minus 11, square root it, and we get the H plus concentration, which is 7.085 times 10 to the minus 6, so that's closest to B. Question 10. What is the pH of 0.46 solution of potassium hydroxide at 298 K? You've been given Kw. So if you're given Kw equals the H plus concentration multiplied by the OH minus concentration. So you've got Kw, you've got the OH minus concentration. So 1 times 10 to the minus 14 Kw equals H plus multiplied by OH minus concentration. You've given OH minus concentration, so H plus concentration is 1.0 times 10 to the minus 14 divided by the OH minus concentration 0.46, 2.174 times 10 to the minus 14. pH is minus log to the base 10 of that, 13.66, which seems reasonable for the pH of potassium hydroxide, which is a strong base. Answer B. Question 11. What is the mass in milligrams of carbon formed when 3 times 10 to the minus 3 moles of propene undergoes incomplete combustion? Well, 2 moles of propene makes 6 moles of carbon, so 1 mole of propene must make 3 moles of carbon. It's in the ratio of 2 to 6 or 1 to 3. So that's the number of moles of propene, multiply it by 3, and I'll get the number of moles of carbon formed. So 2 moles of propene makes 6, 1 to 3, multiply the 0.003, which is the moles of propene, by 3, 0.009 moles of carbon. Moles is mass divided by mR. The mR of carbon is a 12, so 0.009 equals mass divided by 12. Mass is 0.009 times 12, 0.108 grams. If you're taking grams and converting it into a smaller unit of milligrams, you multiply by 1,000, 108 milligrams, or 1.08 times 10 to the power 2. The answer is C. Which compound gives this infrared spectrum? Well, we haven't got an OH, so an OH would be a broad peak here, so we've not got butan-1-ol, and carboxylic acid's got an OH as well, so we've not got an OH. This will correspond to CH's. What have we got? We've got a very, very big peak here at around about 1,600, something like that. 1,680 to 1,750 is a carbonyl group, a C to double bond O. So I'm looking at something like an aldehyde or a ketone, not butanoic acid that's got an OH, not butan-1-ol, which has got an OH, because there's no OH peak. It's butanol is C. Question 13. Which pair of compounds does not form a racemic mixture when the compounds react? So a racemic mixture at equal amounts, equal concentrations of both enantiomers. So if we've got equal concentrations or equal amounts of both enantiomer, then we need a chiral carbon in there. That's a carbon that's got 4 different groups attached to form 2 different kinds of enantiomer. So the question is saying which one hasn't got chiral carbons when it's reacted. So we're looking for something maybe symmetrical, so automatically I'm drawn towards D because I've got 2 methyl groups. So D looks as if it's automatically going to be the answer, although I can talk you through why the others are not. So A, if HCl joins across the double bond by electrophilic addition, then what you've got is you've got a chiral carbon on carbon number 3, I assume, where let's say the Cl goes, so if the H goes on carbon number 2 and the Cl goes on carbon number 3, although it wouldn't matter if it were the other way around, this carbon would have a CH, it's already got one H, it would have a CH, a CH3, a Cl, and then a CH2, CH3. The Cn bonds on with nucleophilic addition. The Cn bonds on with the lone pair of electrons on the C would attack that C plus there, and the delta minus there. The electrons would go onto the oxygen, then it would react with some dilute acid or some methanol to produce H plus. H plus would join on and make an OH, so I'm going to get Cn here, OH, H is already joined and I've got a CH2, CH3, so this carbon would be a chiral carbon here. HCl across the bond, well, the major product would form a CH3 here, where the H joins onto the two H's, the carbon with the two H's already here, and the Cl. This would form a chiral carbon on carbon number 2 because it would have a CH3, a CH, a CCl, and a CH2, CH3, whereas this CN would bond on here and form CCN, two methyl groups, so automatically this C hasn't got a chiral carbon, and the OH would form from the O. So the answer is D, because of these two methyl groups here. This carbon's not going to be a chiral carbon. Question number 14, let's have a look what's happening here. We've got ethane forming chloroethane via free radical reaction involving ultraviolet light and chlorine. Then we've got nucleophilic substitution as the OH bonds to the C of the CH2, that polar bond, and releases Cl minus and substitutes. This is at the OH minus is a nucleophile, an electron pair donor, so we'd replace the Cl here with nucleophilic substitution. We've got a dehydration reaction here where the concentrated sulfuric acid is removing water. It's removing one of these H's from CH3 to make CH2, and on the adjacent carbon removing the OH. So a dehydration reaction, and then we've got Br2 adding with electrophilic addition across the double bond. So which one's nucleophilic substitution? This one here is nucleophilic substitution. Incidentally, it'll be in cold water, otherwise it would be elimination and it would form ethene, but we've got nucleophilic substitution of the Cl. Question 15. Cisplatin is an anti-cancer drug. Which structure represents a stereoisomer of cisplatin? If you have a square planar structure, you can have optical isomers on a square planar structure. I know I've not got a chiral carbon, but a square planar structure like this with platinum in the middle and a square planar structure can have optical isomers. This is the normal form of cisplatin. Cis, incidentally, cis and trans were the old word for E and Z, Z and E. So cis means on the same side, Z. E means opposite. Like the two Cl's, this is cis or Z, and this is E, opposite, or sometimes called trans. So this is Z-platin, in other words, cisplatin. This is the normal kind with two NH3 groups and two Cl's. Now the stereoisomer of this, cisplatin, is transplatin, where they're opposite, almost Z and E. These two are ruled out because the NH2 groups, they don't have NH2 groups, you have NH3 groups in cisplatin. So these two are ruled out automatically. So is a stereoisomer of normal cisplatin. This is normal cisplatin, and this is transplatin, cisplatin, transplatin. Question 16. I've got a Maxwell-Boltzmann distribution of molecular energies. The higher peak curve is at a lower energy because the most probable energy, C, at the lower energy, means that the particles on the whole have got less energy than in the higher temperature curve. The reason the peak is lower in the higher temperature curve is because there's more particles with more energy, and so the line goes higher towards the high energy end. The x-axis is the amount of energy, the y-axis is the number of molecules, and so the area is going to stay the same because in both cases it's the same sample of gas. It's in some kind of vessel, and so it's sealed vessel. Then the number of molecules stays the same. So the area under the curve represents the number of molecules. This is the higher temperature where the peak is lower, and there's a shift towards higher energy, more particles with a high energy. Incidentally, they both go through the origin. So A would be the number of particles, the number of particles with the most probable energy, C, at the lower temperature. B is the number of particles with the most probable energy at the higher temperature, and D is the energy that most particles have, the most probable energy of the molecules at the higher temperature, because along the bottom is energy. So it was always going to be C or D if you knew that the x-axis was energy, and C is at the lower temperature, D is at the higher temperature. V2O5 can be used as a catalyst in the contact process, which is a step in the contact process in which the vanadium is oxidized. So let's have a look at the oxidation state. V2O5, O's are -2, so that's -10. That's +5 for the V, so it's -10 divided by 2 plus 5. +5 and +5 equal the 5 minus 2's. There, and it goes to V2O2, 2 minuses, 4 minus for the 2 O's, so that's in +4. So it's gone from +5 down to +4. So it's been reduced. Let's have a look at this one. Similarly, +4, 2 minuses is -4, so that must be in +4. Here it's gone up to 5, 2 minuses is -10, so 2 V's must be +10, that must be +5. So that has gone up, that's been oxidized from +4 to +5. +4 here, +5 here, so that's a possibility from +4 up to +5, and this is +5 going down to +4, that's been reduced. So it's between B and C. And simply you've got to learn that then, so your answer is C. 2VO2 plus half O2 go to V2O5. That's one step in the contact process. Let's have a look then. The structure for question 18 shows a section of the polymer. So what you've got to do is, if this is an addition polymer, so they've been formed, look at the carbon backbone right down the middle, a very strong carbon-to-carbon backbone, strong carbon-to-carbon bonds, and that's why something like this is not biodegradable, because the carbon-to-carbon bonds are strong. This has been an addition polymer, where short unsaturated monomers with double bonds have broken the double bonds and all joined together. What you've got to do is you've got to spot the linkage, spot where the links are, so the repeating units. So let's have a look at the repeating units. I've got HCF3HH, HCF3HH, HCF3HH. So I've got, that's one link where I've got CH2CHF3, CH2CHF3. That seems to be a repeating unit, and the other one that seems to repeat is CH2CFH, CH2CFH. So I've found the two repeating units. Now I've imagined that they have come from having double bonds. Before the double bonds have broken, they've formed a long polymer, a long saturated polymer with single bonds. I can have a look at this. So this has been CH2 with a double bond, CFH, CH2 CHF, yes, same thing. CH2 CHF is a possibility. It appears in A and D, so it's either A or D. And the other one is CF3H, CHF3, CH2, CH2, CHF3. The answer is A. D is incorrect. The answer is A. CH2, CHF, CH2, CHF, and CH2, CH2, CHF3. The answer is A. Question 19. I've got an equation for reaction between zinc and hydrochloric acid to make zinc, chloride and hydrogen. What is the minimum mass in milligrams of zinc needed to react with 50 centimetre cubed of 1.68 mole per decimetre cubed of hydrochloric acid? I've been given a volume and a concentration, so I need to turn that into decimetre cubed, use my concentration to work out number of moles, then work out that 2 moles of hydrochloric acid react with 1 of zinc, so half it, and then work out my mass from there. So concentration is moles divided by volume. I spotted that because I've got 2 pieces of information about the hydrochloric acid, so it wants me to work out the third unknown. I've got to put 50 centimetres cubed into decimetre cubed. That's a smaller unit value, centimetre cubed, than decimetre cubed. So I'm dividing by 1,000. 50 divided by 1,000 is 0.05. So concentration is moles divided by volume. 1.68 is moles divided by 0.05. Moles HCl, 1.68 multiplied by 0.05, 0.084. 2 moles of hydrochloric acid react with 1 mole of zinc, so over half that divided by 2. Then I've got 0.042 moles of zinc. I know the MR of zinc, so moles is mass divided by MR. Number of moles 0.042 equals mass divided by its MR 65.4. Multiply the two together, 2.75 grams. Taking grams down into a smaller unit value of milligrams, then I multiply by 1,000, 2750 milligrams. My answer is 2.75 times 10 to the power of 3, which is C. An equilibrium mixture is prepared in a container of fixed volume. So I've got an equilibrium reaction here, CO plus Cl2, equilibrium to form COCl. The temperature of this mixture is decreased and the mixture is allowed to reach a new equilibrium. Which is greater for the new equilibrium than the original equilibrium? So, exothermic reaction, so if the reaction is exothermic, that means it's exothermic in the forward direction. So CO and Cl2 forming COCl3. In that direction it's exothermic, in the other way it's endothermic. So if the temperature is lowered, let's think this through, then the reaction will increase the temperature by Le Chatelier's principle. So if you lower the temperature, or try and increase the temperature by surroundings and shift the position of equilibrium to the right hand side to make more heat, to give out heat. So this will not make more CO, so A is incorrect. So the mole fraction of carbon monoxide, if the temperature is decreased, the mole fraction of carbon monoxide, is it going to be greater? No, it's going to be less because the equilibrium will shift to the right hand side. So it'll also make less Cl2, so the partial pressure, that means the pressure of the Cl2, the amount of Cl2 or the concentration of Cl2, the amount of Cl2 contributing to the overall pressure will decrease. So that's incorrect. So that decreases rather than increases. So B is wrong. C, the total pressure of the mixture, is that going to increase? No, it'll make more product. So 2 moles going down to 1, so it's shifting to the right hand side. 2 moles going down to 1 will lower the volume and lower the total pressure, so that's not going to increase. The value of the equilibrium Kp, so how will that affect the equilibrium constant? So the value of the equilibrium constant, making more product, will increase the value of the equilibrium constant because you're making more product, and the equilibrium constant is the amount of product divided by the amount of reactants, or the concentration of the products divided by the concentration of the reactants, or in the case of gases, the pressure of the reactants divided by the pressure of the products. And if you're making more product, then Kp, or the equilibrium constant, will increase. Question 21. In concentrated alkali, propanone reacts with hydroxide ions to form an equilibrium mixture as shown. I've got water made, so it's some kind of elimination reaction where water is eliminated, or rather the H is removed from here. The H is gone and I've made a double bond, so the OH minus is attacking that H to make water, taking the H off. It looks as if the electrons are going from that H. When the OH minus and the lone pair of electrons on the O attacks the H, then the electrons will go into the double bond, and that double bond on the CO is moving. The electrons in the double bond are moving onto the O. So let's talk through that again. We've got a lone pair of electrons on the O attacking that H to remove it. It will form water. The electrons from that C to H bond then are going into a double bond here to form a double bond, so they're moving from here to here, and then we've got an O minus, so it's formed a single bond from a double, so the electrons from the double are moving on to the O to make an O minus and a single bond. So which does not appear in the reaction? A CH bond going in between the two C's to make the double bond? Yes, it will. So the OH minus lone pair of electrons attacking that H to make water, and the electrons from the CH then move in between the double bonds. That's correct. You'll never see that. You'll never ever see that. That's not such a thing. So the oxygen is electronegative, much more electronegative than the C. So you get a delta minus on the oxygen. So it can go the other way. It can go from the double bond onto the oxygen, which is electronegative and withdrawing electrons along that bond towards itself anyway, but it'll never go the other way. So B is clearly incorrect. Let's just check the others through. A lone pair of electrons attacking the H. Yes, that lone pair of electrons attacking that H. It's the other way up. They've moved it upside down for some unknown reason. But the OH minus with the lone pair of electrons attacking the H. Yes, that's attacking the H there to make the water. And the lone pair of, and the double bond breaking electrons going onto the O and making an O minus and a double bond into a single bond is clearly correct. And that will happen because the O is electronegative and withdrawing the electrons in that direction anyway. So your answer that's incorrect is clearly B. Question 21. A tricky question this. The diagram shows a pH curve produced by adding a strong alkali to a weak acid, which represents the buffer. Remember what a buffer is. So we think this through. Maybe it's not so difficult. When we think this through, a buffer is a solution that prevents the pH from rising. So if we're at A and we're adding alkali, then the pH is rising here. So A isn't acting as a buffer because the pH is rising quite quickly when we're adding alkali. C, when we're adding alkali, that rises quickly. So C isn't acting as a buffer because they add a little bit more alkali and the pH goes up. And D, well, I've got nearly pure all alkali here. Your answer is B. So B, because B, even though I'm adding alkali here, the pH isn't going up until eventually I add enough alkali to make the pH go up, and D is nearly all pure alkali anyway. But here you've got a mixture of a weak acid and I'm adding a strong alkali and the pH isn't going up, so your answer is B. Question number 23. Which alcohol could not be produced by the reduction of an aldehyde or a ketone? There's a quick way of doing this. If there's a methyl group at carbon number 2 and there's an ol group at carbon number 2, in other words, those two numbers are the same, where there's a methyl, the ol group, and there's a methyl group also at the same number. So 1 ol, is there a methyl group at number 1? No. 2 ol, is there a methyl group at carbon number 2? Yes, that cannot happen. 2 ol, there's no methyl group at number 2. Pentan 3 ol, no methyl group at number 3. So when you have a methyl group at carbon number 2, and an ol group on the same number, carbon number 2, that cannot happen. It cannot happen because what would it have been? It would have been the ol before it was an ol and reduced. It would have been a carbon to oxygen double bond at carbon number 2. So carbon number 2 would have had a carbon to oxygen double bond. At carbon number 2 there would have been a methyl group at carbon number 1. An ethyl group then at carbons number 2 and 3 and a methyl group. That carbon at carbon number 2 in the middle of a chain would have had carbons either side, a methyl group and a carbon to oxygen double bond. It would have had 5 bonds, impossible at carbon number 2. So the quick way of looking at it is if those two numbers are the same, the methyl group and the ol group, it can't have come from a ketone. Which compound does not show stereoisomerism? So let's draw them out. 1,2-dichloropropene, 1,2-dichloropropane, 1,3-dichloropropene, and 1,3-dichloropropane. Which one does not show stereoisomerism? Well, remember, there's two kinds of stereoisomerism. There's geometrical isomerism, where either side of the double bond you have two groups. So I've got 1, 2, two different groups to the left of the double bond, two different groups to the right of the double bond. So that will show stereoisomerism. It will show EZ isomerism or geometrical isomerism. The CLs have larger atomic numbers. So this one's down and this one's up. This would be E1,2-dichloropropene. This one's got a chiral carbon here. So this can have optical isomerism, a form of stereoisomerism called optical isomerism, because this one's a chiral carbon with a Cl, an H, a CH3 and a CH2Cl. So that will have enantiomers. This one, To the left of the double bond I've got a Cl and an H, two different groups, and to the right of the double bond I've got an H and a CH2Cl. This one is going to form geometrical isomerism. So what have I got? I've got to the left of the double bond I've got a Cl with a larger atomic number than the H, so this Cl takes priority over the H, and to the right of the double bond I've got a C bonded to the C with an atomic number 6, H bonded with an atomic number 1. This group here would take priority, so I've got two groups on the same side. I've got Z13-dichloropropene. Whereas this one doesn't have a chiral carbon at all. I've got a C with two H's, I've got a C with two H's, and I've got a C with two H's, and no double bond, so no free rotation, no lack of free rotation around the double bond, no geometrical isomerism, and no chiral carbon to give an optical isomer. So your answer is 1,3-dichloropropane. The answer is D. 25. Which compound can form a polymer without needing another reagent? So what I'm looking at is I'm looking at two different groups on either end. If I've got two groups the same, then they'll never bond and have a condensation reaction. So I need two different groups, one at one end which will bond with a different group at the other end. So I've got two ols here, a diol, and I've got a dioic acid here. So A and B are immediately ruled out. C and D has got an OH and a COCl, so that's a possibility. This one's got a Cl and a COH. So I need to know what kind of groups will bond together in a condensation reaction. Well, I can have a carboxylic acid and an OH will form a polyester, or I could have an acyl chloride group such as this COCl with an OH, which would form a polyester as well. Instead of it releasing water like carboxylic acid group and an OH, which will release water, it will release HCl as white steamy fumes, but it will form a polyester. Or I could have had a COCl or a COH with an NH2 to form a polyamide with an amide link, but C will work. Question 26. A solution of lead chloride Mr278.2 contains 1.08 grams of PbCl2. So why would they be giving me a mass and an Mr only to work out the number of moles of PbCl2? So without reading any further, let's do that now. So moles of PbCl2, moles is mass divided by Mr, 1.08 divided by 278.2. I've got 0.00388 moles of PbCl2. I've dissolved it in 100 centimetre cubed of solution. That's a bit of a red herring. I've dissolved it in some water. I've made a solution out of it, and in this solution the lead-2 chloride is fully dissociated into its ions. It means that the Pb has formed an ion, and the Cl's, the two Cl's have formed ions, so it will have formed Pb2 plus and 2 moles, 2 lots of Cl minus ions. What is the concentration of chloride ions? Well, for every 1 mole of this PbCl2, when it dissolves in water, 1 mole of this will release 2 Cl minus ions. So the number of moles of PbCl2 is 0.00388. But when it dissolves in water, to make 1 mole of this will make Pb ions and 2 Cl minus ions. Then it makes 2 moles of Cl minus ions from 1 mole of PbCl2. So I need to multiply it by 2, 0.00776, to work out the number of moles of Cl minus ions. What is the concentration? Well, the concentration is moles divided by volume. I do actually need the volume now. So concentration is moles divided by volume, 0.00776. And I need centimetre cubed in decimetre cubed, centimetre cubed in decimetre cubed if it's going from a small unit value to a larger unit value, like centimetre cubes up to decimetre cubed, divide by 1,000. 100 divided by 1,000 is 0.1. So my concentration is moles divided by 0.1, 0.0776. So my answer is D, 7.776 7.76 times 10 to the minus 2. The rate equation for an acid catalyzed reaction between iodine and propanone, there's the propanone, is this. The rate equation was measured for a mixture of iodine, propanone and sulphuric acid at pH 0.7. So immediately I'm thinking, why would they give me pH as 0.7? Well, pH is minus log to the base 10 of hydrogen ion concentration, so they want me to work out the hydrogen ion concentration, otherwise they wouldn't have given me pH. So let's do that first. pH is 0.7 is minus log to the base 10 of the hydrogen ion concentration. So what I do is I reverse both signs, so minus 0.7 is plus log hydrogen ion concentration, and then I do an inverse log to get rid of the log. So I do minus 0.7 is log of H plus concentration, and then do an inverse log or a shift log, depending on your calculator, shift log or an inverse log of minus 0.7, and the H plus concentration will come out as 0.2. Now then, it says nothing changes. In the second mixture, the concentration of sulphuric acid was different, but the concentration of iodine and propanone were unchanged. So this concentration isn't changed. Assuming that the temperature hasn't changed, then the rate constant won't change. So the only thing that's changed the rate equals something that's unchanged multiplied by the H plus concentration multiplied by something else that's changed. If the rate has gone down to a quarter, then the H plus concentration must have gone down to a quarter, because the other things in the rate equation hasn't changed. So if this has come down to a quarter of what it is, then originally, then the H plus concentration must have come down by a quarter of what it was originally, because the other, the rate constant and the concentration of propanone are unchanged. So the new H plus concentration is a quarter of what it was. 0.2 divided by 4 is 0.05. What's it actually asking me now? The new pH, so pH is minus log to the base 10 of hydrogen ion concentration. This is the new hydrogen ion concentration. Minus log to the base 10 of 0.05 is 1.3. So your answer is B. Question number 28. A 385 centimetre cube sample of carbon dioxide. I've got the pressure in kilopascals and I've got a temperature. Was then mixed with argon. I've got a gas constant. So I'm looking at PV equals nRT. And I've been given information about the carbon dioxide. I can work out number of moles of carbon dioxide. Then it's told me the number of moles of argon that I'm mixed with. That's the next stage. So what the mole fraction is, it's the number of moles of carbon dioxide as a fraction of the total number of moles. So my first step is to work out the number of moles of carbon dioxide using PV equals nRT. The R gives me a clue that I'm going to be using PV equals nRT. Let me do spoilers, because I've got centimetres cubed here, kilopascals and 25 degrees C, and they're all wrong. This needs to be in meters cubed, this needs to be in pascals, and this needs to be in Kelvin. So let me show you what I'm doing. I'm taking for carbon dioxide, so for kilopascals into pascals, that's a larger unit than this unit, so I'm going from large unit down to small unit, so I multiply by 1,000 to get small units, large units into small units. 100 kilopascals is 100,000 pascals. Volume 385 centimetre cubed. So to get it up into decimetre cubed, up into a larger unit, I divide by 1,000, so that will be 0.385 decimetre cubed. And then to go up into another larger unit, meters cubed, from decimetre cubed, I divide by 1,000 again, so 0.000385 meters cubed. 25 degrees C into Kelvin, I add on 273, so 273 add 25 is 298 Kelvin. Now I've got all of those in the right units, pascals, meters cubed and Kelvin. PV equals nRT, so pressure multiplied by volume is 100,000 pascals multiplied by volume 0.000385 equals the number of moles, that's what I want to find, multiplied by the gas constant, which I'm always given, 8.31, multiplied by 298. I would always multiply these out first on my calculator so that you don't make mistakes. So 100,000 multiplied by 0.00385 is 38.5, and these two multiplied together, 8.31 times 298 is 2476.38. Now I do n. N is 38.5 divided by 2476.38, 0.0155. That's the number of moles of carbon dioxide, because I've used the data for carbon dioxide. The total moles of gas then, all the moles of gas then together, including the 2.89 times 10 to the minus 2 moles of argon, I add together. So I add the number of moles of carbon dioxide and the number of moles of argon, 0.0444. That's the total number of moles of gas. So my mole fraction of carbon monoxide is the number of moles of carbon monoxide that I have, divided by the total number of moles of gas that I have altogether in the mixture. So 0.155, the number of moles of carbon dioxide that I have, divided by the total number of moles of gas in the mixture. 0.0444 is 0.35, so my answer is A. 29. How many peaks does this compound have in its carbon-13 spectrum? So I'm looking for the number of different carbon environments. That S isn't in the middle. If it were here, it would be different, but it's not. It's not symmetrical in any way. So all of these carbons are going to be in different environments because that S is not forming a symmetrical structure. So I've got 1, 2, 3, 4, 5, 6, 7, 8 different carbon environments, because that S is not forming a symmetrical structure in any way. The answer is D. 30. A student is provided with 5 centimetre cubed of 1 mole per decimetre cubed ammonia solution. So without looking any further, I've got a volume and I've got a concentration. I can work out moles of ammonia. So let's do that now. 5 centimetre cubed up into decimetre cubed, I divide by 1,000. So that's 0.005 decimetre cubed of 1 mole concentration. So concentration is moles divided by volume. 1 equals moles divided by 0.005 decimetre cubed. The number of moles of ammonia is 0.005 decimetre cubed. Let's read on through the question now. The student was asked to prepare an ammonia solution of concentration 0.050 using this solution. So I know that the number of moles hasn't changed, but the amount of water has changed. So in the new solution, the new concentration is 0.05. 0.05 is the number of moles. Well, I'm using this ammonia solution. I'm not changing the number of moles, I'm just changing the amount of water. So 0.05 is 0.005 moles divided by volume. Volume, therefore, is 0.005 divided by 0.1 decimetre cubed, which is 100 centimetre cubed. So to get decimetre cubed into centimetre cubed, and all these are in centimetre cubed, I have to multiply by 1,000. To get decimetre cubed, a large unit value, into a small unit value like decimetre cubed, I multiply by 1,000. 0.1 multiplied by 1,000, 100 centimetre cubed. Now, you may be tempted just to go for C, but read the question carefully. What volume of water should the student add? You had 5 centimetre cubed originally, you now want it to be 100 centimetre cubed, so you need to add a further 95 centimetre cubed. The answer is B. Question 31. Once you're over the first part, the next part is just whether you've revised thoroughly and you know the colours of these ions. The solution absorbs light with wavelengths red, yellow and green. So if it's absorbing red, yellow and green, the colour that it's not absorbing is blue. So if it's coming through the solution and the solution is absorbing the red and the yellow and the green light, then blue must come through and hit the retina of your eye. And so this solution that's absorbing red, yellow and green light but not the blue will appear blue. So which ion is likely to be blue? So then you just need to know your colours. A dichromate ion is is orange, and Fe2 plus is light green, and Fe3 plus is orange, yellowy orange, and a Cu2 plus is blue. So the answer is D. A reaction is exothermic and has a negative entropy change. Which statement is correct? Tough this, a tough question. Let's do spoilers and I'll show you the reaction and I'll show you why it's C. Delta G is delta H minus T delta S. The reaction is feasible if delta G is negative. So we've got to get a negative value here for this reaction to be feasible, for it to possibly go ahead. Delta H is exothermic. It tells you that here. An exothermic reaction is negative. So delta H is a negative value. Minus T delta S. Well, delta S is the entropy change. That's negative as well. So if delta S is negative, a negative means that this is a plus. So minus temperature multiplied by a negative value, a negative value minus T delta S. This is a plus value here. Yet delta G needs to be minus. So if this is a positive value, and this positive value is bigger than delta H, which is a negative value and a very positive value will be positive overall. So you're looking for this to be very small. So this positive value needs to be small so that the negative value of delta H means that the delta G is negative. So you're looking for a small temperature. A small temperature. The reaction is feasible below a certain temperature. The answer is C. Question 33. Phenyl ethanone can be prepared by the reaction between ethanol chloride, CH3COCl, and benzene, C6H6, and it forms this chemical, phenyl ethanone. In preparation with an excess of benzene, the mass of ethanol chloride, Mr 78.5, was 5.7 times 10 to the minus 2 kilograms. So I've got the mass, it's in kilograms, but I can easily convert that into grams by multiplying by 1,000. So and I've got the MR, so I can work out number of moles of benzene, and therefore I can work out the number of moles of phenyl ethanone, which will be the same, 62% yield. I can work out the mass. Okay, so for ethanol chloride, moles is mass divided by MR, so the mass is, the moles equals, the mass is 0.057 kilograms, so because it's 5.7 times 10 to the minus 2, multiply that by 1,000 to get kilograms into grams, multiply by 1,000, 57 grams. So I've got 57 grams of ethanol chloride, Mr 78.5. So number of moles is mass divided by Mr, 57 divided by 78.5 is 0.726 moles. I've got 0.726 moles of ethanol chloride. That will react with 0.726 moles of benzene and make 0.726 moles of phenyl ethanone and make 0.726 moles of hydrogen chloride. But it's the phenyl ethanone that I want to concern myself with. So I've got the number of moles of this. So let's say that we've got 62% of this. 62% of this. Well, let's do the, I tell you what, let's do the grams first. So let's turn it into grams first. So number of moles is 0.726 moles of phenyl ethanone. I've got to work out the MR. Well, I've got 1, 2, 3, 4, 5, 6 carbons, 7, 8 carbons, so 8 12s. I've got a hydrogen on each of these corners here, not one on that one. I've got 1, 2, 3, 4, 5 carbons and 3 more, 5 hydrogens and 3 more. That is 8 hydrogens, so 8 ones and a 16. So my MR is 120 of my phenyl ethanone. So number of moles, 0.726, is mass divided by 120. Multiply the two numbers together. I've got 87.12 grams of phenyl ethanone. That's assuming 100% yield. 82.7. I've only got a 62% yield, so I multiply by 62 and divide by 100. I've got 54.01 grams. B. 130 centimetres cubed of oxygen and 40 centimetre cubes of nitrogen at 298 Kelvin and 100 kilopascal pressure were placed into an evacuated flask. Okay. And I have therefore got, what is the pressure of the gas mixture? I've got pressure, I've got volume. I've not got gas constant, interestingly enough. They usually give me the gas constant, but they haven't done in this case, which is very, very rare. But I'm going to have to use PV equals nRT. My total volume of gas is 170 centimetre cubed. I need to get that into metre cubed. I've got it in Kelvin, that's correct. I need to get this into Pascal by multiplying by 1,000. Let's do spoilers then, let's see. So my pressure is 100 kilopascals. To get it down into a smaller unit of pascals, I'll multiply by 1,000, so I've got 100,000 pascals. My total volume, it doesn't matter that I've got a mixture of gases, the total volume of the gas, so for this system in here I've got a total volume of 170 centimeters cubed. So I'm going to work out the total number of moles of gas, oxygen and nitrogen combined, 100 centimeter cubed. To get that into meters cubed, I have to get it into decimeter cubed first by dividing by 1,000. So I'm going from a small unit into a larger unit, centimeter cubed into decimeter cubed. Then to go up into meter cubed again, to go up again into a larger unit, I divide by 1,000 again. So 170 centimeter cubed divided by 1,000, 0.170. Divide by 1,000 again, 0.00170 meters cubed. My temperature already in kelvins, that's fine. Pressure times volume equals nRT. 100,000 is my pressure in pascals, multiplied by the volume, 0.00170 meters cubed, is n number of moles of combined oxygen and nitrogen gas. I'm not given the gas constant, but I'm given it earlier on an earlier question, so I can easily look that up. 8.31 multiplied by 298, which is my pressure. I'd always multiply these out first, and then multiply these out first, and these two multiplied together equals 17. These two multiplied out together equals 2476.38. Divide the 17 by the 2476.38. The combined number of moles of oxygen and nitrogen that I've got is 0.00686 moles. Now then, all I've done then is I've put these into a new flask of a new volume. The number of moles hasn't changed. I've put the oxygen and nitrogen together, that number of moles, in a new flask. So, and I've not changed the temperature, 298 Kelvin. I've just got a new volume, so I can just work everything out again. So pressure times volume equals nRT. My volume is 0.5 decimeter cubed. I need to get that into meter cubed by dividing by 1,000. So decimeter cubed up into meter cubed, I divide by 1,000. That's 0.0005. Pressure times volume equals nRT. Pressure, I need to find the pressure. So pressure I don't know. Volume 0.0005. I've just worked that out. N is the number of moles. That hasn't changed. All I've done is just change the size of the flask. So the number of moles I've worked out originally, 0.00686. Gas constant hasn't changed. Temperature hasn't changed. Let's multiply all those out. 16.99. Important to multiply them all out first on your calculator, then you're less likely to make a mistake. Pressure is 16.99 divided by 0.0005. 33976 pascals. All of these are in kilopascals, so to get pascals up into a larger unit value of kilopascals, I have to divide by 1,000, 33.976. 33.976 kilopascals. The closest one to that is 34 kilopascals. Two significant figures. My answer is C.